Okay, so this is my great pleasure to introduce our next speaker, Stephen Simpson, who will talk about Ramsey quantifiers and arithmetic, I guess.
Well,
Thank you, Steve. Go
well,
ahead.
really, I don't have much to say. I only have about 5 slides, one of which is this title page, and it's just uh, well, okay. So to take up some time here, let me say that thank you to Roman for organizing this and whoever else organized it. And thank you to Jim for being Jim. And thank you everyone else, many old colleagues. I don't mean old colleagues, I mean former colleagues who I haven't been in touch with for years are showing up here. Julia Knight and Carol Wood and lots of other people. It's really great to see all of you. Um, Ali, the fantastic talk. Um, and you know, I'm not really in the area of models of arithmetic or models of pan-arithmetic or models of set theory or anything like that. Uh, but uh, Jim, uh, I had a very early collaboration with Jim. This was uh, I was doing a postdoc. Well, after getting my PhD in 1971, I went. Uh, uh, can you all hear me? Can you all understand me?
Yes.
Yes, yes.
Okay. The I just got some message from Zoom asking me if I was speaking English. Okay, so yes, I am speaking English. Um, um, anyway, uh, what was I saying? I got my PhD in 1971 from Gerald Sachs at MIT, and I stayed for a year at Yale as a postdoc, and Manny Lerman and Jim were there as my colleagues, along with Abraham Robinson, of course, who was the top logician there, and uh, and Manny and Jim both influenced me tremendously. Um, and Later, I'll talk about a joint paper that, well, at the beginning of this real talk, the real content of this talk, I'll talk about a joint. Actually, almost the entire talk is about a joint paper that I wrote with Jim in later in about 1980. But they were great colleagues, and I don't know, Jim, did you participate in the ping pong games with Manny and C.T. Chong?
I don't remember, but
Okay.
I did play ping pong, but
Okay. Well, you
I
probably
haven't
did
played
then.
in a
So
long time.
yeah, me neither. Okay. So anyway, we had a great time. All
Yes,
right.
Steve, this is
Now,
Manny. I think Jim participated a few times, but not as regularly as the rest of us did.
yeah, that was my recollection.
Where was the ping pong table?
It was across the street in some building and across the
Oh,
street from the math department. It wasn't
oh,
in the math
I
department.
don't remember. Yeah.
Okay.
Okay.
I don't remember where it was either.
Okay.
All right. Anyway, um, all right. So let me, next slide, please. All right. So what I want to talk about is this paper by myself and Jim on the role of Ramsey quantities in first order arithmetic, quantifiers in first order arithmetic. This was inspired by Angus's paper, Ramsey quantifiers in arithmetic. Angus wrote this paper and did a lot with Ramsey quantifiers in arithmetic. And he let us see a draft of this paper, and then we wrote our paper answering some of his questions, or some questions suggested by his paper. And I'll say more about his paper and our paper later. But okay, so let me first tell you what I guess the main result of the paper from the viewpoint of models of arithmetic. So let PA be the usual axiom system for Peano arithmetic. The standard model is the natural numbers. We expand the language of Peano arithmetic by introducing for each K a Ramsey quantifier, which binds, this is a quantifier which binds K number variables. And the semantics for this in the standard model is very simple. It says that it says QK phi means that phi holds for all K tuples of some infinite subset of the natural numbers. All K element subsets. Those are required to be distinct elements, or you could take them to be in order A1 less than A2, etc. But that's the Ramsey quantifier. QK means that the formula phi induces a partition of the K tuples of natural numbers into two pieces, phi and not phi. And this says that the quantifier QK says that the phi side of that partition contains an infinite set. In other words, that partition, Ramsey's theorem applies to that partition. So we know that either phi or not phi contains an infinite set. It contains all the K tuples from an infinite set, but this says that it's on the phi side. Okay, so that's what this Ramsey quantifier means. It's just a I hope that's clear, because I'm not going to give it many technical definitions in this talk, but that's what it means, is that QK of x1 through xk means that there exists an infinite set such that the following holds for all K element subsets of that set. And this is in the standard model. The semantics for the standard model are very clear. Now, if you have a non-standard model of Peano arithmetic, the semantics for QK are not so clear. You could take it to be the some collection of subset. In other words, instead of an infinite set, because we don't know what we mean by an infinite subset of a standard of a non-standard model of Peano arithmetic. In other words, it could mean an unbounded set, or it could mean so the semantics. It could mean literally an infinite set, which might be bounded, or it could be an unbounded set with some additional properties. Um, we don't know what the semantics of QK is in non-standard models of arithmetic. So you have to specify a semantics. But the axioms for PAQ, that is pan-arithmetic um, with all these Ramsey quantifiers, the axioms for it are clear, and I'll spell out the axioms in a minute on the next slide. And this theory, PAQ or something like it, was introduced by Angus MacIntyre, building on a paper of Mogador and Malitz, which was about Ramsey quantifiers in general. Well, other kinds of generalized quantifiers. But he specifically looked at the PA case of this Ramsey pan arithmetic supplemented by Ramsey quantifiers. That's what MacIntyre was looking at in that paper. And he proved a completeness theorem for PAQ. But the proof wasn't really a proof because it used a special set theoretical hypothesis, namely Jensen's diamond, the diamond principle of Jensen, which is true if V equals L, but it's not it's not true in all models of ZFC. So that was MacIntyre's contribution. And then Jim told me about his work, and he taking off from that work of MacIntyre's, he gave a better set of axioms for PAQ and a better version of the theorem. And in particular, he eliminated the diamond hypothesis. So those results by Schmerl, the better set of axioms, the better version of the theorem, and eliminating the diamond hypothesis, those results of Jim were in section 2 of our paper. That was section 2 of the paper. Okay, and so that's now I'm ready to tell you more details about what Jim actually did. So the axioms of PAQ, Schmerl's set of axioms, look as follows. The axioms of PA, of course, plus induction for all PAQ formulas. Of course, PA includes induction, but only for formulas in the language of PA. And PAQ, we've extended the language, we've extended the logic actually by adding a new quantifier or a set of quantifiers QK. I should say that I'm just going to give the axioms in the case K equals 2, and that's not really a loss because the same thing holds for any K, for K greater than or equal to 2. Everything I'm going to say also applies to PAQK, but I'll just restrict it where K is arbitrary, but I'll just restrict it to K equals 2. So what the axioms for PA plus induction for all PAQ formulas, and then the following axioms which sort of give you obvious properties of the standard interpretation of Q. What the property 2 here is, or axiom group 2 is that if you have a formula two formulas, phi and c, and phi implies c for all x and y, then, and if there exists a witness set for phi witnessing qxy, phi xy, in other words, an infinite set, whatever we mean by an infinite set, but in the natural numbers, this is truly an infinite set. An infinite set such that all pairs have the property phi, then the same holds for property C, the second property. So I hope that's clear what I'm saying there. If it's not clear, stop me, because I don't have much to say in this talk, really, mathematically. Okay, axiom group 3 says if you have a witness, if qxy, phi xy holds, then of course there must be an infinite set witnessing that. And then you can take one, then there exists an element of that set such that that set minus that element is still a witness set. And that's what this axiom is saying. So every witness set for qxy, you can find there exists an element of it such that subtracting that, removing that element leaves it still to be a witness set. All right, and then the fourth axiom group, let's see, it says that if some definable property defines an infinite set, then and for all elements, for all pairs in that set, phi holds, then it's a witness set. So these are all trivial properties of the standard interpretation of PAQ in the standard model of arithmetic. But we're just writing down obvious axioms for them. Okay, now, so that's PAQ. Now, I want to state Jim's completeness theorem for PAQ. Of course, you have to say what we mean by a non-standard model of PAQ. And a model of PAQ obviously consists of a model of PA plus some collection of subsets, infinite subsets or unbounded subsets of that model. And we say by a strong model, we mean a model where all unbounded subsets of the model of PA we can use them all. We're using them all to interpret Q. So in other words, the model consists of a model of PA plus the power set really of that model. And that's what Jim calls a strong model. And then the completeness theorem, Jim's completeness theorem for this PAQ, is that a set of sentences in PAQ is in the language of PAQ is consistent if and only if for all it has that set of sentences has a kappa-like strong model for all uncountable regular cardinals kappa. Okay, So it's a very elegant completeness theorem, and you don't need Diamond to prove it, and it gives you results about kappa-like models for all regular cardinals kappa. So I'm not maybe I should define kappa-like, but it's been discussed in previous talks. But let me just say it in words. A kappa-like model is a model of PA where the cardinality of the model is kappa, but every initial segment of it is cardinality less than kappa. All right, so that's Schmerl's completeness theorem. Now, I want to go back and tell you what my contribution to that paper was, because I'm eternally grateful to Jim for getting me interested in models of arithmetic, and or encouraging my interest in models of arithmetic, because it plays a role in my work, although I'm not a specialist in models of arithmetic like Ali and people like that. So now let me go back to McIntyre's paper. McIntyre, in his paper, he discusses the Kirby-Paris theorem and the Paris-Harrington theorem. These are theorems that say, both of these theorems say that certain transparent finite combinatorial statements are not provable in PA. In other words, before that, we knew by the Gödel incompleteness theorem that there was a sentence in the language of PA which you couldn't prove in PA. That's true, but you couldn't prove it in PA. That's the Gödel incompleteness theorem. But there were no examples of, I'm exaggerating a little bit, but there was no examples of finite combinatorial statements that are sort of have a combinatorial flavor that just are easy to understand, like the finite Ramsey theorem. The finite Ramsey theorem is a finite combinatorial statement, but that's provable in PA. What Paris and Harrington did was they modified the finite Ramsey theorem to get a version of it which is not provable in PA. And it was just a slight modification. It looks a lot like Ramsey's theorem, the finite Ramsey theorem. And the Kirby-Paris is has a different flavor, but Goodstein sequences and all that. But though what happened was that around this time, historically, this is when people began to discover that the incompleteness of PA is not just chatter. It actually applies to real theorems that can be stated easily in the language of PA or similar languages, finitistic theorems that look like they should have a finitistic proof, but they don't. And a proof in PA, they don't even have a proof in PA, which goes beyond finitism. So that was a big development at that time around 1979. And so McIntyre discusses this theorem and similar theorems, and he says he says pretty explicitly that that's his reason for being interested in PAQ, because PAQ, the Paris-Harrington theorem, is provable in PAQ. It's not difficult to see that. So and what he says is that he expresses Angus expressed the hope that the combinatorial incompleteness phenomenon, the finite combinatorial incompleteness phenomenon, PA, would be handled by introducing some extra quantifiers, like Ramsey quantifiers. And so he had the feeling that PAQ would be enough to settle most finite or maybe all finite combinatorial statements that are of combinatorial interest. So, let's see, I should also say that other authors later produced similar finite combinatorial statements, also with a Ramsey flavor, that are not provable in systems stronger than PA. And at the time, I was very interested in subsystems of second order arithmetic. So the point is the subsystems of second order arithmetic give you a way to measure the logical strength of a theorem via reverse mathematics, and I was interested in that. So at the time, that was very interesting to me. So this situation was the motivation for McIntyre's study of PAQ, which is much stronger than PA. I'll let Angus comment on that if that was really what he was interested in, but it says so in the paper. So it says so in Angus's paper. So it became, to me, it was desirable to compare PAQ with subsystems of second order arithmetic from this perspective. And so we solved this problem by proving that the sentences in the language of PA that are provable in PAQ are exactly those that are provable in a certain subsystem of second order arithmetic, namely pi11 comprehension, if you know what that is. Let me just say that pi11 CA0 is now well known as one of the big 5 subsystems of second order arithmetic in reverse mathematics, as studied in chapters 2 through 6 of my book on subsystems, my book, Subsystems of Second Order Arithmetic. By the way, that's the worst book title anybody could come up with. Every word in that book, well, I'll comment on that later when I have the title on the screen. But anyway, these 5 systems, these big 5 systems, pi11 CA0 is the strongest of the big 5 systems, and they are recognized as being important because they play a role in reverse mathematics. So the answer to the question is yes, PAQ proves a lot of finite combinatorial theorems which are not provable in PA, but no, it doesn't prove all finite combinatorial theorems that are combinatorially interesting and not provable in PA. So there's you can measure exactly how much of that is unprovable. All right. So now this is my last slide. I just want to comment on some of the literature here. First of all, McIntyre's paper, which I've already commented on, was inspired somewhat by Magador and Malitz, a paper of Magador and Malitz on generalized quantifiers, and specifically they introduced something like Ramsey quantifiers, but they didn't specialize to PA. They didn't look exclusively at PA. And then another book I'd like to mention, and I have it here. You see, it's a big fat book. This is the book Model Theoretic Logics, edited by Barwise and Pfefferman. It's more than 900 pages. It's huge. It's a huge book. And Jim, this is sort of the broad topics of generalized quantifiers and so on. Jim has a chapter in that book which has been mentioned. I mean, I think Jim mentioned. I think Ali mentioned Jim's chapter in this book. Then another paper of Jim was later in 1986 published in the Transactions of the American Mathematical Society, and he extended my result about Pi-1-1 comprehension to get some to Pi-1n comprehension for any n, so much stronger systems of second order arithmetic, and using similar ideas involving sort of hyper Ramsey quantifiers. So that's why that's a significant extension of what Jim and I did back in around 1980. And finally, I want to mention my book, Subsystems of Second Order Arithmetic, because as I say, this is the basic reference on reverse mathematics, and I give a lot of credit to early influences for getting me interested in this subject. And it took me decades to to finally publish the book, but there it is. It was published in 1999. So, okay, so thank you for your attention. And that's all I have to say. I guess maybe I haven't used up all my time.
Thank you, Steve.
Have I used up all my time? I guess.
Well, it's hard to say. Well, we started a little late. No, the time's up, but
okay.
You didn't
right.
go over. No, this was all very good. So, any comments, questions?
Oh, Angus, don't you have any comments? What were you thinking of when you wrote that paper on Ramsey quantifiers? You don't remember.
Angus,
I'll tell you the
you're
truth.
muted, Angus. If you're
He
trying
remembers, but he's muted.
You're muted.
I don't really know what was the question. What was I thinking of?
No.
What? I don't.
Oh, I was asking Angus what he was thinking of. What were you thinking of, though? Since Angus is muted and he's.
So we will.
I don't know. I don't know. I guess it was just to get rid of the diamond in Angus's theorem.
Okay.
I don't know. But I was going to say something about to Steve. You said you commented that that title was the worst title you could come up with.
Oh, yes.
And you didn't comment on that.
Oh, yeah. Subsystems of second order arithmetic. Think about it. Every word in that title is a downer. Subsystems of second order arithmetic. Arithmetic is just baby mathematics, right? So, I mean, it's ridiculous.
Okay.
But So that's the worst title I could have come up with.
Well,
But it's descriptive of what the book is about.
Yeah,
that's interesting.
see, it seems accurate.
Accurate. Okay.
Can I say
Okay.
something about the question earlier from Roman?
Yeah,
Sure.
Yeah, I mean, can you hear me? Yeah.
Yeah,
Yes.
yeah.
now we can hear you.
I mean, I sort of associate. I mean, I was thinking a lot about Paris Harrington and Paris Kirby and so on. I had a lot of contact with Ken McAloon and others. I think in the case of, so I knew a lot about Ramsey quantifiers and I knew about generalized quantifiers from much before, but I associate this whole thing with a conference in Houston where I think Harvey was present. Harvey usually has a good effect on me in making me think about something. And I associate my work in this thing with the Houston airport. I think as soon as I got away from the meeting, I started to think about it on the way back to New Haven. It made perfectly good sense to me. I mean, I had tremendous respect for what they were doing with the Ramsey ideas in arithmetic, and it just seemed natural. And I had been exposed to the kind of Polish work on generalized quantifiers before and stuff like that. So I didn't expect miracles, but I got very carried away by it. The funny thing is, I mentioned in my talk today that this work I did on Tenenbaum's theorem for quotients of non-standard models of PA by primes. That was somehow provoked by Harvey too, but just because of the way he kept going on about Friedman's theorem about initial segments. I mean, I knew how to prove the theorem, and others did too. But I don't remember having any. Harvey and I got on very well together. I mean, we argued a lot with each other and so on, but I think we do have, I think, affection. I haven't seen him for a long time, unfortunately, but I don't recall anything from the meeting in Houston where he actually said anything that provoked me. But I know that it was at that moment that the idea began to move rapidly. That's about all. Otherwise, I agree very, very much with what Steve has said in the whole thing. It corresponds to the way I was thinking about these things. Yeah, definitely.
Yeah, definitely. Harvey had a role in getting me interested in subsystems of second order arithmetic, and how the idea that you had to ask a basic foundational question is, what are the right axioms for mathematics? And you have to calibrate what kind of strong principles you need to prove theorems.
Yeah.
That if you to the extent that you need them. So that's the idea of reverse mathematics.
Yeah, I mean, when I was working on Tenenbaum thing for primes and so on, I mean, I was also there. You see, it took me a long time to understand axes. Paper Kreisel gave it to me when I was at Stanford. It was just appearing. I spent a great deal of time, although I knew a lot of number theory then. And I mean, when you see just the beauty and the tremendous power of Bayes' Riemann hypothesis and Chebotarev's theorem, it seemed natural to me to take these as, I mean, it's not exactly reverse mathematics, but similarly, these were the things which had tremendous power. I mean, what Axe did with Chebotarev theorem in that Annals paper is just utterly fantastic. Every single one of these problems was out of reach until Axe came in. But it's different. I mean, I don't see any other axioms that one might like to add to PA or something, arithmetical axioms. I mean, there might be some. I haven't seen them. But it's not the same philosophy, of course, as reverse mathematics. But it is connected with finding some kind of viable system of axioms. I mean, of course, the system from Bayes and Chebotarev is viable, but one would hope there are others. There are much deeper conjectures than those nowadays in 21st century mathematics and so on. But they're, I mean, desperately difficult to get at by proof. And there's also this issue. I mean, it doesn't maybe have any genuine philosophy, but I mean, I've always been interested in the issue of, I guess this was from Kreisel's influence, that I've actually taken, I mean, I understood the Wiles theorem, and I knew Wiles for a long time. And it seemed to me to make sense to look for a proof just in PA of the Fermat theorem. Now, it's a big task, but a lot of the discussion there was some discussion from the logic community, but most of the time people they seem to have missed the basics. I mean, this modularity condition and so on that came into the proof that because if you did it naively, it looked like higher order. Many logicians more or less went on record as suggesting that Fermat might need that. On the other, what they didn't know, and I worked out for myself, and what others worked out, is that the actual modularity thing is a very simple arithmetical statement.